skerm af nie, so ek is nog onsigbaar.
Daar sou staan 'n praat en hulle
Hulle hoef my nie te hoor nie. Hulle het vir hom hoor, party mense is belangriker as anders. Jy weet, almal is gelyk, maar party is net 'n bietjie gelyker en Adam is gelyker, want Adam kom hoogs aanbeveel by his students and people that I know. Thank you so much for coming to talk to us. I've been wanting to have a talk on the geology of Magaliesberg for years, and at last it's coming together and we've got you. Thank you so much. This seat's hot in the front as well. I think we must take the fan away from them and can put it here. But did they switch this one off? Because is that right? So without any further ado, I'm going to leave to Adam to start, and so that we're sort of on time. Otherwise, I'm the one that makes us late. Thank you again.
Thanks very much, Michelle. Thanks very much for inviting me along. It's great to be here. I work just across the hill at the University of Pretoria, but I live right here in Regentdale. So every morning when I drop my kids at school in Queenswood, I've got to trail up and over Tom Jenkins. And when we speak more loudly, sorry, this is not connected to a loudspeaker system. This is just for the live streaming. So I'll speak as loudly as I can.
Sorry, can you put the record down? There you go.
Super. So I have to drive from here in Regentdale across Tom Jenkins, across the hill, down Eastwood Street to the university, and there's always traffic. There's traffic on Gordon. Every time you're trying to travel north-south in Pretoria at rush hour, it's a pain. And the reason that we all get stuck in traffic if we're driving north-south is because of the geology. I live on the other side of Regentdale, just on the Peony Bridge. That's also part of the geology. And the Magaliesberg is all part of the geology as well. We've got 3 ridges there. This ridge behind us, the ridge at Peony halfway through Regentdale, and then the Magaliesberg Mountains. 3 ridges all running east-west, and that's all part of the same story. So when Michelle asked me to give a talk on the Magaliesberg Mountains alone, I thought, actually, that's not going to really do it. It's going to be like you're at a book festival or a book signing, and an author reads you one chapter out of a book in order to get you to buy the book and get all the rest of the story. I don't think I could just give you the chapter on the Magaliesberg without considering the whole story. So I'm going to try and do everything tonight, the whole story of why you get all of these east-west running ridges through Pretoria and all the way up to the Magaliesberg, because it's all part of the same story. So when you talk about the Magaliesberg, I assume that what you're thinking about is this ridge that goes from Pretoria and keeps going all the way past Hartbeespoort down and out ultimately to beyond Hartbeespoort out to Rustenburg, and then it's a bit of a bend and goes up towards Sun City. That's what most people in Pretoria think about when they're talking about Magaliesberg. But that is also just a small part of the story, because when it stops there on this map, when people's mental map of where the Magaliesberg are stops, the rocks actually keep going. They keep going all the way up to the north, and then the Magaliesberg rocks, the same rocks that we have here, head off all the way eastwards, and then it curls around and comes all the way back and joins up here. So the Magaliesberg story is not just this part. Those rocks are more continuous. So if I take that map that I've just lost there, it fits into this geological map in this red box. And the Magaliesberg goes along here. That's where we saw it sort of curving up to the north. And then bits of it keep going around here. You can see it goes all the way out to Botswana. And then it picks up again, goes all the way up past places like Abazimbi. You lose it a little bit here, and then it picks up again over here by Leidenberg, and then ultimately comes all the way back to Pretoria. So it's a much bigger set of rocks than you might have originally thought. And we've really got to consider all of this area if you want to know the whole story. if we want to tell this story completely, we've obviously got to go back in time to the period when the Magaliesberg rocks were first deposited. They're sedimentary rocks, so they began their life as sediment. It's a sandstone or a quartzite, so it began its life as sand and turned itself into rock over the last, well, since it first formed. So if we go back to when the Magaliesberg Mountains was first formed, we're going all the way back to when it was sand. And if we go back that far, and exactly how far back that is I'll get to, but South Africa looks very, very different. In fact, South Africa didn't basically exist. This is that red box that we were looking at in the previous slide. Just to go back. My mouse instead. Oh, there it goes. So it's gone by 2 now. Okay, so this is the whole area where the Magaliesberg was deposited, but that's just a small part of this country. But we're going back so far that much of what we see here did not exist at all. If we go back sufficiently far, we're going to see what the geology of this area was like and just how small the crust was that makes up southern Africa. So this is a geological table. We've got today up here an ancient is down there. So if you want to tell stories, we're going in that direction. Most people, when they're reading a story, will start at the top and gradually work down the page. Geologists work differently. They start at the bottom and work upwards. And there's a very good reason for that. That's because if you're putting down layers of strata, the oldest ones are at the bottom, and they get gradually younger as you go up. So typically geologists will work up a page rather than down a page. So if this is old, that's the Cambrian. All of these terms you might be familiar with. Children would like this one, that's the Jurassic, the Cretaceous. This is where dinosaurs roamed the earth. So where in this does the Magaliesberg fit in? How far back from today do we have to go until we find when the rocks, the sandstone rocks of the Magaliesberg was soft sand and first getting deposited? Well, I'd be lying a little bit, because this is not actually complete. If you look in terms of times, that's the day, that's the end of the beginning of the Cambrian, and there's a bit of time before this, which is known collectively as the pre-Cambrian. So we can actually take this a bit further back. And this next slide will show just how far back we go. There's the rest of it. All of these terms that most people are familiar with, like the Jurassic or the Silurian or the Ordovician, that's just the period in geology which is known as the Phanerozoic, where you get fossils. So it's sort of the top bit that's divided very, very accurately based on which fossils were alive at the time. And all of those names, going all the way back to the beginning of the Cambrian, are merely that part of Earth's history. The pre-Cambrian, actually far from being just a little bit before the Cambrian, is actually about 70–80% of Earth's history is all before you get any fossilized life in the planet, or any multicellular life forms anyway. So when I ask where on here do we appear, it doesn't. It's much, much older than the Cambrian. So we can go all the way back. That's now 1,000 million years. That's 2,000, or in other words, 2 billion years. And by now we're getting to the time where the Magaliesberg were first formed. So this is the entire history of the planet, for that matter, the entire history of the solar system. The Earth forms just over 4.5 billion years ago. We're at about 2.2 here. So we're going halfway back into the history of the planet. These are phenomenally old rocks. I studied geology as an undergraduate in the UK, and there we get tremendously excited if we were on rocks as old as the Ordovician or the Cambrian. So we're just there. Then I came to South Africa 30 years ago, and suddenly the rocks were this old. In fact, if you go to Barberton in Mpumalanga, some of the oldest rocks in the world, they are that old. Nothing really survives from down here, they've all been lost. There's a couple of bits of minerals that have been found that do date from way back here in the Hague, but things as old as Barberton are about as old as you can go back. But we're still very, very far back. Geologists descend on South Africa from all over the world because of the very, very ancient nature of the rocks here. So it's places like South Africa where geologists know about the early history of the planet. So this is how far back we're going. And the story that I'm telling is sort of evolving from down here up to about 2 billion years. So let's get back to this map that I showed earlier. We know that we're looking at this little part here. This is where the story is going to play out. If we go back 2.5 to 2.0 billion years ago, that's 2,500 to 2,000 million years ago, then what did South Africa look like? Well, as I said earlier, very, very different. If you look at the ages of many of these rocks, especially around here and there, they are younger than that 2 billion year period. So they didn't exist then. So if we start to look at rocks that are older than 2 billion, we can start to get a picture of how extensive the crust was back then. Oops, sorry. So there's our box again, and this red line would be indicating how extensive the continental crust was at that time. So that's the size of the landmass that's now grown slowly over the intervening time to give us the continent of Africa. So it's a tiny little bit of continental crust. If you're across this line, there was no continental crust there. So that would instead have been oceanic crust. Continental and oceanic crust have very different properties. Continental crust is made up predominantly of granite. And that's a really buoyant rock. Okay, if you chuck a lump of granite in your swimming pool, it does sink like a stone. But in terms of its density, if you have a cubic metre of granite, it weighs about 2.8 tonnes. Or if you have a cubic centimetre, that's 2.8 grams. If you compare that to oceanic crust, that would weigh over 3 tonnes for a cubic metre. So oceanic crust is much heavier, and it has a tendency, because of its weight, to sink back down into the mantle. It can erupt at mid-oceanic ridges, that sort of environment, and then after a couple of 100 million years, it will just sink back in because it's so heavy. The granites that make up continental crust, because they're so much lighter, once they're formed, they tend to bob around at the surface like a cork. So you don't subduct, you don't have any continental crust anywhere on the planet ever sinking back down into the mantle, so it never gets recycled, unlike oceanic crust, which just sinks back in. So once this continental crust is formed, it can be added to, it can grow, but it won't sink. So that's why all these thousands of millions of years later, all of that crust is still here, and we're now living on it. So it's places like this, these very, very early formed continents, these small bits of continental crust, they're known as cratons. This is where people come to study ancient rocks, and that's why Victoria has rocks of such age, because it's one of the very, very earliest formed bits of continental crust. As I said, it's called a craton, and the name that geologists give to this little landmass is called the Kaapvaal craton, because it's occupying the former Transvaal and the former Cape area. So even though politically all of those names have changed, we still stick to our guns in geology, and it's still known as the Kaapvaal craton. It's a sort of mixture of Cape and Vaal. So there's the Kaapvaal craton again. You can see the edge of it. That's meant to be the same line that I drew on the previous map. And you can see that our geology that we're discussing here in the Pretoria area is thoroughly slap bang in the middle of that bit of continental crust. So it would have been ocean floored by dense oceanic crust all the way around, with this one lonely little bit of continent floating around on the surface of the Earth. So I've probably given you the impression I've been talking about the density of, or the lack of density of continental crust, that it's always going to be bobbing up to the surface, it will always be above sea level. But that's not actually the case. If you think about continental crust today, even though generally speaking it's above sea level, it can just sink in a little bit under sea level. So it tends to bob up and down. And so it could start sinking down in places to below sea level, and obviously then the sea would encroach over it. Also, sea level goes up and down as well. Climate. If you've got a period of glaciation, then sea level tends to drop because so much of the water is sitting at the ice caps. And then when that melts, it can rise again. So you have sea level going up and down, and you have the continental crust bobbing up and down as well. So if you think of places like the Black Sea in Europe, it's tempting to think, oh, that must be oceanic crust, it's below sea level. It's actually continental crust that's just sagged down below sea level, so it floods over. And something similar to that happened here on the Kappa crater. So that's where our story begins. When this part of the Kappa crater, and actually down here on the western side as well, that just began to sink down below sea level. So that's where we're going to start our story. The technical name for one of these bodies of water that's floored not by oceanic crust but by continental crust is something called an empiric sea. So the Black Sea in Europe is a modern day example of an empiric sea. Oh, that's not good. Okay. Mind that cable on the floor as well.
I think we've got some empiric chairs. Submerging chairs.
So, as I said earlier, geologists work in a funny way. They go from the bottom to the top. Because if you think of this continental crust starting to sink, have a basin form, and then you get a layer of sediment filling in that basin. And then as time goes by, and it keeps sinking, another layer would then fill on top of it. So you go from oldest at the bottom, gradually getting covered over, and the youngest one at the top. So this story that I'm going to tell you starts here at the bottom, and we go gradually up top. And the Magaliesberg is towards the end of the story. That's where the Magaliesberg fits in. So before we get there, we've got to do all of these older chapters. And interestingly, there's these things in there called angular unconformities. You can think of those as a break in the subsidence. So we have fairly continuous subsidence, which means you get the story filling it from bottom to top. But then every now and then the whole thing lifts up. If you're lifting up, then you're not sedimenting because you haven't got a basin anymore. And in fact, you might lose some of the record. Some of those earlier formed rocks might get stripped away, but then it sinks again. And then that gap between sedimentation, where you might have erosion and loss of layers, that's what's called an angular unconformity. So we've got a few of them here. So it's not continuous deposition in this empiric sea on that little crater. There are breaks in it where you get a bit of uplift and a bit of erosion, which is all quite good for Pretoria, actually, as you'll see. So we're going to tell the story, go from the bottom to the top. So we'll start with these things called protobasinal rocks, the black reef, genus fault group rocks, with the breaks in between, and then the Victoria group, and then this thing called the Bushveld complex on top. So this is collectively known as the Transvaal supergroup. So this is a picture that I took out of a textbook, which many you've seen actually. It's a very popular book. It's one I use for the first years at university. This shows again that same Transvaal crater. And by the time of this, it's actually collided with the Zimbabwe crater on another very, very old bits of crust. And every now and then, just like today, when continental crust collides with other bits of continental crust, for example, India colliding with Asia, with the Himalayas, something very similar to that would have happened between the Transvaal and Zimbabwe cratons. So on that northern edge of the Transvaal craton, where these two cratons collided with each other, you would have had something very similar to the Himalayas. Difficult to imagine now, because the area we're talking about here, that's Polokwane. So this is the Limpopo area, flat as a pancake now. But back then, it would have had these huge mountain ranges running along it as a result of that collision. The other thing that happens as a result of that collision is that if you get away from this mountain range, the rest of the crust starts stretching as a response. So that's the first thing that happens to start our story, that you get stretching north to south and a set of faults running east-west. And those centre part of that fault would have dropped down, much like the East African Rift Valley. If you think about places like East African lakes, where you get these long linear lakes, that's because you've got a low-lying area bounded by a fault either side of it, and it fills up with water. So something very similar to that is happening at the beginning of this Transvaal supergroup when our story starts. And that's where these proto-basinal rocks fill in. Quite limited in distribution, only within the bounds of those two faults. But the sort of rocks that would be deposited there are the ones that we now get at places like these sandstones and quartzite that you have here in the three Rondavels. These are rocks called the Voltberg group. With some of my students many years ago who decided they would go beyond that point for the photo opportunity. All of these are those proto-basinal rocks at the start of things happening in this part of the Transvaal crater. And then, instead of having mechanical breaking along those faults, the next thing that happened was the whole of the crater began to sag in under sea level. And you can see the story beautifully illustrated in the bottom part of the Transvaal supergroup. The first thing that you get after those proto-basinal rocks is a conglomerate. This is called the Black Reef Formation, and it crops out not very far from where we are, a little bit further to the south from us, but this outcrops all the way around the basin, all the way around the craton. And if you've got a conglomerate like this implies that you have to have water flowing powerfully enough to be carrying in these big chunks of grounded quartz. These have been carried down a river. A river is the only place where you can expect the water to be flowing powerfully enough to bring in lumps of quartz. Some of them are about this sort of size. Yeah, that's a powerfully flowing river. So the first thing that we see is rivers flowing over the Transvaal crater. And then just above that are these rocks. Now this is a mudstone, so that's a lot less energetic. Water's flowing more slowly. And you can more or less make out there are little squares in there. See all those little squares? Those are where there used to be salt growing. So the salt's now gone, but salt grows in a cubic shape. The way that the sodium and the chloride moves together, it produces little cubes of salt. The salt has vanished, but what it means is that the water that was across the surface here was salty. So you can see what's happened. You started with rivers flowing down towards the sea, but then the ground sunk some more and the sea came up to meet it. So now we're on the coast. That's why we've got salt crystals growing in amongst the mud. So we're beginning to see the picture of the ground slowly sinking down into the sea. We're going from rivers to the coast. So if we go to the next layer up, which remember are the next oldest, the next youngest ones, things change again. We're going to actually sink below the sea. This is not Pretoria, but it's how Pretoria would have looked in this next stage. These are very strange things. These are called stromatolites. This is Shark Bay in Australia, and it's a very weird place. What's growing in here are little single cellular bacterial organisms, and they photosynthesize, but they're not very good at coping with desiccation. Fortunately, they're right on the coast, so twice a day, roughly, up comes the sea and they get drenched in water, and they do start to dry out. Before they all die, up comes the sea again at high tide. And so they stay desiccated. The water can only be shallow because they're trying to be photosynthesizing. They can't live in deep water because there's not enough sunlight that percolates down so that they can photosynthesize. You don't see much in the way of these stromatolitic colonies of cyanobacteria anymore because things like to eat them. Here in Shark Bay, the water is particularly salty, and the sorts of things that eats those little single cellular organisms just die in that salty water. So the environment here is a lot like the environment would have been in Pretoria all those years ago, because there was nothing that had evolved to eat them back then. So they had complete freedom to grow, to reproduce, to keep growing up through successive layers up towards the sun every year, because there were no higher organisms that might have come along and eaten them. This was it. Single cellular organisms are the only thing existing. There were no snails, there were kinds of things that eat these today. So this place in Australia, Shark Bay, because of the salinity of the water and the inhospitable nature, it's mimicking how it would have been back in 2.2 billion years ago in the Pretoria area. So can we see these same organisms, or colonies of organisms, in the rocks around Pretoria, which are obviously recording going not from rivers to mudflats, to now an intertidal area, or at least just below the sea. Well, these are the sorts of things that you get in these rocks. You can see all of these little domes. This is actually across, taken further west from Pretoria, but you can see the tops of these domes around the Pretoria area. These are fossilized stromatolites, exactly the same sort of organisms that we saw in that most recent photograph in Shark Bay in Australia. And they're a little bit different in places here because they get huge. There's not really much of a scale in there, but the wavelength of these is about 5 meters. These are huge colonies. And everywhere you go across this area that began to flood over, because the whole area is just sunk below sea level, it's perfect. There's no deep water. Everywhere is within that photic zone. So these things, there's nothing going to eat them, and pretty much the whole craton is the perfect environment, just below sea level. So they just grew and grew and grew. And luckily for us that they did, because stromatolites, they're obviously photosynthesizing, and so they release in massive amounts, because it's such a huge platform of these organisms, they're producing this nasty toxic gas into the atmosphere and contaminating the atmosphere, and that toxic gas is, of course, oxygen. So these rocks here in Pretoria, they're the ones that are responsible for oxygenating our atmosphere. And you can see it in the geological record, but rocks at that are on the continent, terrestrial rocks, tend to be rusty after this event, demonstrating that there's that atmospheric oxygen. So the rocks, these carbonate rocks, full of stromatolites, they're cropping out up in the Irene area, and they are really very, very important for the evolution of our planet. So you get different shapes and different sizes and different depths. So there's about 100 meters. Below that, then they starts getting a little bit too dark for them to grow. So most of them grow in very, very shallow water indeed. So the fact these are so widespread means that our continental crust has just sunk below sea level. So let's go up to these are the rocks of the Malmani subgroup, which I might show. So these are the sorts of rocks that you might see if you go just to places like Krunkler Reserve. That's also full of these carbonate rocks. You can see stromatolites there, and you can give them a word of thanks for producing more oxygen. So let's now go up a layer. The water continued to deepen, so that kills off all the stromatolites. And instead what happens is that some of the oxygen that's being produced by the stromatolites combines with iron and magnesium that's dissolved in the water, and then it precipitates. So on top of those carbonate layers with the stromatolites, you then get a layer of ironstone. So this is called banded iron formation, which is a bit of a mouthful, so people just tend to call it BIF, which is easier to say. And that's still there in places, but fortunately not here in Pretoria. Remember what's coming up next at the top of the Penge formation is an angular unconformity. So once the basin has deepened and you start to get these iron deposits forming, there's then a period of uplift. And some of these rocks got stripped away, including these rocks in the Pretoria area. And as I said, it's a good thing for Pretoria that they did, because there's nothing to be mined here. If it hadn't been, we have to go back several slides now, if it hadn't been for this angular unconformity, we would have iron mines here in Pretoria. That level of iron-rich rocks, the Penge Formation, would still be here, and we have places, mines like Tabazimbi or Sishen, they're mining these rocks where they didn't get stripped away. So fortunately for us, there was localized uplift and localized removal of these rocks, fortunately saving us from having massive iron mines here in Pretoria. So this is how far we've got so far. What we've been talking about thus far has been the Geology group, this little wavy line, that's the angular unconformity. But then the basin all sank back again after this period of uplift and erosion. And so now we're beginning to start the story right here in Pretoria once more. We've got more sinking in, so more sedimentation. And these are all the various layers going from old to young in this renewed period of sedimentation. You'll see the Magaliesberg is right there at the top. So what are all these different layers? Well, basically what's happening during this period of time, after that uplift and stripping away of those Penge Formation rocks to relieve us of any iron deposits, is that the sea level just keeps going up and down. So if the sea level is up, then the Pretoria area would have been flooded over, deep water. So you would get deep water rocks, deep water tends to flow very slowly, so you can't wash in large things like pebbles or sand grains, and instead you get this gradual, slow deposition of mud. So you get a rock that's shale today. If, on the other hand, the sea level drops, then the area is going to be exposed to shallow water, maybe coastal water, and maybe rivers as the sea level continues to drop, and then it will rise again. So you might get shale from when it was deep, covered by sandstone from when it was shallow, covered by shale again from when it was deep. As the sea level goes up and down, the size of the sediment that can get washed over an area varies, and so you get these different layers of rock. So, shale, sandstone, shale, sandstone, shale, sandstone. To complicate that pattern a little bit, halfway through all of this, there was a big volcanic eruption. So that's the Heckport Formation, sitting there. 2,222 billion years ago, that's when all of this area was covered in lava. So it's a fairly straightforward pattern of sea level going up and down. If sea level is up, you get shale. If sea level is down, you get sandstone, with the exception of the Heckport Formation when it all just flooded over with lava anyway. So you get these contrasting types of rock, all in layers from old to young, of which the Magaliesberg is pretty much the youngest one in this area. All happening throughout this big area that's wobbling up and down as the sea level rises and falls. And then, after this period of oscillating sea level, we need to talk about this thing called the bushveld complex. Something big is about to happen, which really changes the story a lot. So that's where the bushveld complex goes. You can see where all of these earlier rocks have been deposited. In blue, those are the carbonate rocks and the ironstone rocks. And then sitting on top of those, in that area there, that's where the alternating layers of sand and shale start building up, with a lava flow in there as well, sitting on top of them. And then there's this thing called the bushveld complex, which squeezes in amongst all of that. So let's talk about the bushveld. What goes on? It's staggering. The bushveld complex is a magma. So this is molten rock that comes down from in the mantle, and it rises up and pushes itself into all of these other rocks that we've been talking about. And this is called an intrusion, basically magma forcing itself into other rocks, maybe 10, 11, 12 kilometers below the surface. And intrusions are not uncommon. You get them all over the world. But the bushveld complex is uncommon because of its massive size. It's about 400 kilometers east to west. Similar sort of size north to south. And the thickness of the magma, the thickness of the intrusive rocks, that alone is 11 kilometers thick. It's the world's biggest intrusion that has layering in it. It's colossal. Because it's so big, you get these pulses of magma coming up and refilling, and then it starts to cool down, and certain crystals will grow at certain temperatures. Crystals tend to be denser than the magma from which they formed, so then they settle down. And you get layers building up at the bottom of the magma chamber. And some of those layers happen to be of very high economic value. So things like the platinum and the chromium and the vanadium that they're busy mining all the way around this area of Rustenburg, for example, and out towards Leidenburg, all of those elements are forming by settling within this big magma chamber. But the other more important thing for our story here is how dense that rock is. We argued that granite is about 2.8 tons per cubic meter. This is about 3.5. It's really heavy stuff. And it pushes its way into the surrounding rocks, including the Magaliesberg Formation and all the other rocks in this area. And it's this big heavy weight. And so what it does, as it pushes in, it actually then starts sinking in. And all of those rocks that we've been talking about, all of those horizontal layers of strata that have been building up as the sea level's gone up and down, they start getting dragged down with it. So we've got these alternating layers of shale, sandstone, a bit of lava in there, then shale, sandstone, shale. All of that begins to lose its horizontal orientation and sag in towards the middle. So instead of being flat, these rocks sink in northwards. Here in Pretoria, if you go out to Rustenburg, they sink in towards, so that they're facing towards the east. Out here in the Leidenburg area, they've sunk in so they face west. And up here in the north by Tabazimbi, they've sunk in so that they then face south. So instead of being horizontal, they're sort of forming this kind of basin shape, sinking in towards the middle. So those once horizontal layers have now gone in towards the centre of the bushveld complex. Here you can see it in a bit more detail. We're here in Pretoria. In brown, these are all the rocks that we've been discussing, the Pretoria group, the Transvaal supergroup. And it's these green rocks that are the real heavy ones. You can see that they force themselves in, the magma squeezed itself in just above the Magaliesberg formation, and then as it sank down, it dragged the Magaliesberg formation down into an angle as well. So they all dip north here, dip east there, south there, and dip west there, sinking in sort of like a rim of a bathtub, I guess. And these are some of these really dense rocks of the Bushveld complex. As a general rule of thumb, the darker coloured rocks are, the more dense they are. And these are chromium layers, and that's really heavy stuff. These are a bit more pale coloured, but overall, the whole thing is very dense, and you can see how it's built up in layers. Nobody quite knows why, but some of these layers split. They know that they accumulated on the bottom of our magma chamber by the crystals settling down by gravity. But why there should be these weird splits in the layers, nobody quite knows. It's a very unusual place. But they certainly did form at the bottom of one of these magma chambers. So this is how it now looks. Here you can see a lot of the rocks we've been talking about. There's the carbonate rocks with the stromatolites in. They would have been horizontal, forming on the floor of the sea, but now they're tilted in. All of the rocks on top of that, that's a shale, that's a sandstone, that's a shale, that's a sandstone, there's a couple of others on top of this picture. But now they've lost their horizontal orientation, and they've tilted over towards the Bushveld igneous complex. So that's it, pushing down, dragging these rocks down with it. So if you go to places like Rustenburg, which is probably the nicest place to see this, all of these layers that you can see dipping very, very steeply in towards the right-hand side of that image, they're bedding plates. So they would have been horizontal before that dragging down towards the Bushveld. So the Bushveld rocks are on the right, and you can see how they've tilted, in this case, about 50, 60 degrees towards the centre. Here in Pretoria, that angle of tilt is only about 10, but it's still pretty significant. So this is why we have this very distinctive topography here in Pretoria. We have this pile of rocks that alternate between being quite hard and being quite soft. Shales are really soft. Sandstones can be very hard because they're just made up of quartz, which is really resistant to erosion. So once you tilt them and then start eroding, the erosion takes place at different rates. The sandstones will only erode very slowly, and the shales will erode more quickly. So that's why we keep getting these ridges through Pretoria. And in fact, it's the rate of erosion of the sandstones is made even slower by the heat of that big intrusion of the Bushveld complex, which metamorphosed the sandstone, made it recrystallize, and turned it into a very, very tough resistant rock called a quartzite. So I just went on Google Earth yesterday and drew this picture I annotated this oblique image, just so you can see there's the Magaliesberg formation. So this is north up to the right-hand side. There's the Bushveld complex, which has dragged the Magaliesberg down from horizontal. This is the next layer down, that's the shale of the Silverton formation that forms the whole Wood area. We are presently there. There's a ridge, get my bearings, just to the north of us, that's the Gasport Ridge. That's the previous sandstone layer. Go over the ridge to University of Pretoria, for example, you'll look back down into a low-lying area. That's where the lavas are. So that's recording the level at which there was volcanic eruptions. And then if you keep going southwards, you get back into another quartzite layer and you get the Tambo Hill Ridge. So all of those layers now tilted, so that's why we keep getting these ridges, and this is why I keep getting stuck in traffic. Because if I live here and I work there, I've got to get across this ridge, which is there because the sea level dropped 2.2 billion years ago. So let's take us, this is really all about the Magaliesberg Mountains and about what you might see there. You now know why the Magaliesberg is there, because of a drop in sea level, and it became a much more of a beach-type environment rather than deep water environment. You know why it's forming a ridge now, because it's differential rates of erosion between the shales and the sandstone layers. So let's have a closer look at it. Firstly, I've been calling it sandstone, and it's not. It's quartzite, but it used to be sandstone. What's happened is that the sand grains, as they got heated up by the presence of that magma body only just above them, literally only 100 meters or so above it, the heat of that magma chamber, which would have intruded way over 1,000 degrees centigrade, it started to force, it basically shook the little silica grains around so much that they then grew new crystals. This is very common in geology. If you heat a rock up, it will undergo a process called metamorphism and grow new crystals that are stable under the elevated conditions. Usually the reason that a rock is getting heated up is because it's getting buried. So if you bury a rock, it will undergo metamorphism. But if you bury a rock, you're also squeezing it. So usually temperature and pressure increase together. And that really messes a rock up because the pressure just squeezes it. If you think about the situation here in the Magaliesberg, the conditions are a bit different because the heating is there because of the intrusion, not because of burial. So you get all the elevated temperatures, but not the elevated pressures. So you get metamorphism, but weird metamorphism, because it allows for the preservation of all of those original sedimentary features from back when it was a sandstone. So it's a very, very unusual rock. You can see that the quartz grains here are 2 to 3 centimeters in size. They were never washed into place as a sandstone when they were that big. The river wouldn't have had enough power, or the beach wouldn't have had enough power to do that. All of these massive chunky quartz grains have grown in place from the sand using the same silica, the same atoms, but so yeah, these quartz grains are secondary. They've come after deposition and after it turned from sand to sandstone. The heat then turned it into quartzite, and you can still see these same features from back when it was a sand and was a sandstone. So you can still see the bedding plates nicely in there, despite the fact that it's metamorphosed. And amazing things have survived this history. These little tiny structures that you see here that are so delicate, that have survived all the way through deposition, burial, turning into sandstone and then heating up and turning into quartzite, these are ripples from way back in the day when this first formed on the beach in Pretoria 2.2 billion years ago. And they're still there today. Amazing preservation because of the lack of pressure during the heating up. They allowed all of these little structures to stay there. And you can see amazing things in amongst these fossilized ripple marks. The shape of the ripple mark tells you a lot. If it's an asymmetric ripple, it's got a gentle side and a steep side, that means water flowing in one direction. That runs the rock, the sand grains up into an asymmetric ripple. If the ripples are symmetrical, that means that the water was going in both directions. So that would mean waves lapping in and out to build up symmetrical ripples. Sometimes you can see evidence that the water, the tidal area dried out for a while. So you can see desiccation cracks, just like you get in a puddle today. If you leave a puddle out in the sun, the mud shrinks, and you get all of these little cracks forming in the puddle. You've got the same shape and size cracks forming there, suggesting that every now and then the water evaporated away. So these sorts of outcrops, which are pretty much everywhere in the Magaliesberg, I'm sure you've seen them there, tell you an awful lot about the paleo environment. There you've got little cracks in the middle, and then you've got ripple marks superimposed over the top of it. So it dried out quite a bit, but then the water level rose again and the waves started lapping in and out, and you started building up more ripple marks there. So all sorts of things you can tell by looking at some of these features that are preserved on the bedding planes. The reason that those cracks in there, between the crests of the ripples, have got preserved is also probably an interesting story. Why wouldn't these cracks get destroyed once the water level came up and the current started blowing sand around? Well, the reason for that, we think, is because there were those little single cellular organisms, the cousins of the ones that formed the stromatolites, and they're probably growing in little mats in the gaps between the ripples, and so they preserve those sort of sticky, sort of slimy mat structures that grow in between the ripples, and they help to preserve the features in between. So there's evidence that there's microbes growing in amongst these as well. This is obviously long before that Cambrian explosion of life when you start getting multicellular organisms. That's not going to happen until about 600 million years, and we're talking 2,200 million years. But, of course, these are single cellular organisms, so that doesn't really count within the Cambrian explosion of life, which is multicellular organisms. So all sorts of interesting structures in those Magaliesberg rocks, which are preserved in there despite the long and unfortunate history that the Magaliesberg mountains have had of being baked and tilted and all sorts of things. There's also a whole load of deformation in those mountains as well, which is a bit more recent. So firstly, if you look at the crest of the Magaliesberg range, there's Magaliesberg Dam, there's the crest coming along, this is sort of Mount Arant area, and then there's Rustenburg is just up there to the north. That's that turn where the Magaliesberg mountain ranges goes up north through Rustenburg naturism. But you'll see that the ridge is not continuous. It jumps around a bit, and that's because of faulting. So if you follow it along here, when you get to Magaliesberg Dam, it suddenly jumps, it's like a little tooth that's falling out. The ridge crest suddenly jumps into the middle of Magaliesberg, and then it jumps back again to where it was. So it lines up, and there's that little bit that seems to have sort of almost fallen southwards. And then it's fairly continuous along, and then you get to this area. This is Elephant's Neck Dam, and it just stops altogether. But then it resumes up here. Again, that's a fault, and you can actually trace that fault going all the way up there. And what you could do effectively is take away that fault. You could slide that back down. And how far you've got to slide it till the ridge crests meet is about 11 kilometres. That's a pretty big fault. 11 kilometres of displacement. It wouldn't have done that all in one go. It would have done it metre by metre, but it would have kept moving incrementally, like the San Andreas fault, for example. In California, every few hundred years there would have been an earthquake and it would have jumped a few more meters. So that displacement you see is collectively over a long period of time. But you can very neatly see how those would have fitted back together again. Let's just look at some of those in a bit more detail. This again is Magaliesberg. There you can see the Magaliesberg ridge going along. And there's that bit that's dropped. It's tempting to think that this is slid southwards like a tooth. In fact, what's happened is it has moved down. It's moved in like that. We talked earlier about the East African Rift. That's where you have rocks in the middle that slide down two inclined fault planes that dip towards each other. And that's what's happened here. The reason that it looks as if it's headed south is because those rocks are dipping. So if you imagine that this was a more continuous layer going up into the sky before erosion, these have actually dropped from above down in that. And the rocks that were here are now well buried down deep in the ground. So that's it's called a graben. You have two faults passing through there. This block in the centre is dropped towards the centre of the earth. Those are the two faults. And that's why the Crocodile River was passing through this area. It was exploiting one of these faults, I think this one. So all that the engineers had to do in the early part of the 20th century was put a little down wall there, and the Magaliesberg does all the rest of the job. It acts as the dam wall for most of Magaliesberg Dam. Just put a dam wall across one of the faults, the job done, the water will start backing up and flooding the whole area. So there's a bit of an engineering significance of the Magaliesberg there as well. Fortunately, the faults are not active anymore. They haven't moved in a long time, because you might be thinking, is it safe building a dam wall directly on a fault? But yeah, they are very much inactive faults, so I think that people living here in Brits are probably okay. Then you can see that same displacement. You can see the ridge coming along, there's Harties, and there you can see that block that has apparently moved southwards, but it hasn't. Those rocks would have been up here, they've dropped down. The rocks that would have been here are now deeply buried. Just another view of the same thing. So that previous photograph was taken from, I think probably from the cable car here, looking across in that direction. Just in the distance, see where it's starting to curl around towards Rustenburg. There's the dam wall sitting in there. You can see how the Magaliesberg does a very good job of holding back the water. That's just a little model that I made. So there's your two main faults, the Magaliesberg faults and Commando neck faults, and there's a couple of them parallel as well that don't stand out quite so nicely. You can see the layers gradually dropping in. Where are we now? Oh, now we're in Rustenburg. So there you can see this is all, Rustenburg is sitting up there. There's that Rustenburg fault passing through, and you can nicely see the rocks have slid horizontally in that direction. The west side going north, and the east side heading southwards. What's also nice there is that the rocks are folded as well. So you've got an overfold there, and then which is an anticline, it's a bit like that. And the top of it has been, sorry, no, actually, that's Rustenburg. Yeah, I'm looking south eastwards there, not northwestwards. Yeah, so there's Rustenburg. This is the big nature reserve there. That's Oliphant's Neck down there. So there you can see that overfold, the top of which has been stripped away. And then next to it, you can see it's a syncline. So you've got a situation that looks a bit like that. And if you go here to Rustenburg Nature Reserve, you can also see the overfold anticline there, the syncline there in that big clay area. And so those two folds, once you slide the rocks back, the two folds match up, because anticline stops there, starts there, the syncline stops there, starts there. It's the same fold that's been torn in two by the fault. And you can pick it up on both sides of the fault. So if you want to know how far it's moved, then you just basically measure from the anticline here to the anticline there. And that's the 11-kilometre difference that I mentioned earlier. Same sort of thing. So there we're looking southeast. There's the rest of the Magaliesberg heading off towards Magaliesberg. And yeah, there's Rustenburg. Also a city that it now is, a few of the mines. Obviously, that's the Magaliesberg. We go down in the strata, we go further to the south, so then that's shale unit, and then there's the next sandstone unit. If you go the other side of Magaliesberg, then we get into the bushveld complex. So all of this is the heavy weight pushed down and tilted Magaliesberg towards the middle. There you can see all the various platinum and chromium mines dotted around the Rustenburg area that are exploiting those layers of platinum and chromium rich rocks in the bushveld complex. The last thing I want to talk about is the beautiful cliffs that we get there. We were talking about these earlier, and they're a bit of a mystery, really, because they are very, very deep cliffs, and you can see that they are often running parallel to each other. In fact, there seems to be parallel sets. Got a set going that way, and a set going that way. And these are joints in the rocks, and they're cracks that are getting exploited by flowing water. Water's going down into the crack, percolating through and eroding the rock either side. But they just get deeper and deeper and deeper. But for me, the strange thing is that as soon as you get onto the bushveld complex going north, you lose them. So cliffs should erode backwards. They should basically start downstream and work back upstream, but these seem to do exactly the opposite, and I just don't know why. They're falling very, very nicely in the quartzites, but as soon as you get off the quartzite, you lose all sense of the fact that you've got that erosion and that downcutting. But they are in parallel sets, and that's mimicking the direction in which these rocks have been stretched in the past. So you get these sets of cracks, which are now being beautifully exhibited by these very, very deep cliffs. And yeah, they're tens and tens of meters deep. So somewhere down here, underneath the water, there's a little tiny microscopic crack that's responsible for enhancing the erosion, which is then leading to the very, very deep cliffs. If you're in some of these cliffs and you look, you will see these little tiny cracks sometimes that are happening to form. That's it.
Adam, thank you so much. Any questions? You have the floor?
You're first, yeah.
Professor, I just want to know, Pretoria is about 1,300 meters, I think, above sea level together. Only when the sea level rises and falls, it's tens of meters, not in hundreds. What caused this whole Cape Val area to fall so much to be under the sea level at that time?
That's a good question. I think the height that we are now is strangely high. Pretoria as a city is about 1,000 meters higher than you would expect in the middle of a continent. In fact, if you look at the topography of Africa as a whole, you can see that the whole of southern Africa is now pushed right up about 1,000 meters higher than it ought to be. But that's actually quite a recent thing. Southern Africa was lifted up 5 and 20 million years ago. It went through 2 different pulses of uplift. And each time it's gone up, you can see the effect of this on the rivers. The Orange River, for example, where you get all of those alluvial diamonds that De Beers are after, that's had to cut down successively deeper the Orange River as it flows towards the Atlantic Ocean in the last 20 million years, because Africa's just kept lifting up and tilting, and all the water's now flowing down towards the Atlantic Ocean rather than the Indian Ocean. And as it's cut down, it's happily for De Beers left behind all these river terraces full of diamonds for it. But the point I want to make is that the elevation of Pretoria and all of the high fat is geologically very, very recent. And nobody's terribly sure why it's done this, but it is enormously high. To the point where I know at the university, in the build-up to Olympic Games, you keep getting Olympic swimmers descending on the university sports grounds because we've got one of the highest Olympic-sized swimming pools in the world, and they want to do high-altitude training here. So that whenever they get to Rio or wherever the games happen to be, they've got all this extra oxygen. So yeah, we are bizarrely high here. So the fact that Pretoria is high now is recent, and it doesn't imply that Pretoria and all of the high felt region was high back in the past. continental crust I've been talking about has been buoyant and floating up, but it's only just buoyant. Most continental crust is only a few tens to a few hundreds of meters above sea level, with this part of the world being a strange exception in recent years. So when you've got continental crust being only just enough buoyant to be sitting above sea level, it doesn't take much in change of buoyancy or mantle dynamics or sea level going up and down in order to flood it over. So that probably answers your question really. So how come that flooding wasn't this elevated back then? We're only just at being above sea level. So a little bit of variation over the floods.
The Malmani Dolomites.
Yeah.
How far up to north are they stretching, and are they linked with the Okavango Delta?
So the furthest north that I know of Malmani is just to the north of Tabazimbi, and then they seem to pinch out. So the fact that they don't get developed further north than that implies that that's sort of the edge of where this was beginning to sink down. The Okavango Delta, though, again, much younger. In fact, the Okavango Delta is still forming now. And what they think the Okavango Delta is representing, so we talked about the Brits Graben, how a block has sort of dropped down. Something similar is happening in the Okavango. A block has dropped down, so the water's flowing into it, but it's the other fault, the other side, is basically acting like a dam wall. And there's so much evaporation there that the water, once it hits that, the dam wall of the fault block, doesn't need to go elsewhere. It can poof off into the atmosphere. So something is making the rocks in that part of Botswana fault, stretch, and the blocks drop down. And it's done that very recently. And what they reckon is that is the East African Rift Valley coming in this direction. So the spreading in the East African Rift Valley is you're basically splitting Africa apart. It started way up in the north in Ethiopia. It's been coming gradually further and further south. And at the moment, people would usually agree, get to the southern edge of Lake Malawi, and that's it. That's the end of the East African Rift System. But geologically, it's not, because we're picking up more and more earthquakes in Botswana, in the Chapis area, in South Africa, and in Beira as well on the Indian Ocean coast in Mozambique. So if you look at the map of the East African origin, it keeps splitting. Sorry, not East African origin, the East African Rift. It splits around Lake Victoria, for example, and then it comes back together and goes down through Lake Malawi, and it seems to be that splitting again. One split is going to go off through Botswana, and another split is going to head to the coast in Mozambique. And so the Okavango Delta is evidence for that East African rift starting to work its way through Botswana. So it's really very, very recent. It's modern news. Whereas, of course, the Cheneysport group rocks, the Rahmani group rocks that we talked about, they're 2.2 billion years ago. So that's a very different story. That's very, very ancient sinking in of the crust. So I think there are two different stories, both of which involve partial flooding of bits of continental crust, but I think they're unrelated to each other. Yeah.
Thank you so much for the very interesting talk. I just wanted to ask about the Bushveld complex, the magma pipe. Do any geologists know like where it was or how big it was? Like what scale are we talking?
Huge and probably multiple pipes, and they're all buried down beneath it. The problem that geologists face is obviously a lot of these things that they guess are there, because you have to have some way of bringing the magma up towards the surface. So there must be some sort of plumbing underneath it that's bringing it in. But you can't get down to look at it directly because it's well deeply buried, many tens of kilometers. So what they rely on would be geophysics, basically using the sound waves bouncing back off, or maybe the magnetic variation in rocks, so you can image what's going on under the surface really quite successfully. the whole petroleum industry, for example, is based on clever geophysicists figuring out what's down below the surface using these geophysical methods. The problem with the bushveld complex is it's such a massive, heavy, dense lump of rock that it's very, very difficult to image through it. So they don't quite know where the location of these pipes is, as far as I know, but they have to be there somewhere. And there's probably 2 or 3 of them coming up in certain locations, because the bushveld complex, I've sort of described it as one big lump, but it's actually 4 separate lobes in different places. So there's the eastern lobe, which is the one that goes through out to Leidenburg. There's the western lobe that goes out through Rustenburg. Then there's the northern limb, which is going up towards Mokopane area, all the platinum mines you see there. And there's even the southern one, which is actually covered over, nobody knows very much about it. That's sort of in the Bethel area out in Himalaya. So it's come up in these 4 different zones, so probably each one has its own little feeder pipe underneath it. But the scale of it is really staggering to have that much magma pushing into the crust, pretty much all in one go. If you age date the crystallization ages, you'd expect to see at the bottom the crystallization age, which you can work out from radiometric age dating, to be significantly different from the crystallization ages at the top, when finally the whole thing cooled off. But the difference in age is as little as 1 million years. So it all happened all in one very quick go. So no wonder the crust just gave up and sank. The other thing, of course, is that if you're pushing all of that magma through the crust itself gets hot, it gets plastic. So it gets so weak with this big heavy weight on top that it was never going to be able to support the weight of it. It all just sank in, giving us the ridges and valleys that we see around the bushveld complex today, meaning I can't get to work. Yeah.
Is the last related to the bushveld complex, or is that also more recent?
It's younger. It's, I think, 1.2 billion years old. But there's that very close and very suspicious proximity. If you have to go back a few slides. Yeah, it's have to go back lots of slides. The fact that it's come up right in the middle of the bushveld complex has intrigued geologists. So the difference in age and the difference in the chemistry, they're very different rocks chemically. That would be basically it's unrelated geochemically. But I think there is a relationship in terms of the control of where it would come up. There it is. The earlier question was asking about where the pipes might have been that gave you all of these massive rocks in the bushveld complex. There's that southern lobe down here, as I said, it's largely buried. There's the eastern side, sorry. There's that northern limb and the eastern limb. And there's a kind of vague axis running right the way through the middle of this, running along there. So that might be a control over where the pipes were that brought up the massive amounts of magma for the bushveld complex. And lo and behold, there's Pilanesberg sitting right on that axis. So it's a sort of a yes-no answer. I don't think that the volcanism that caused the Pilanesberg complex is related in any way to the bushveld complex because there's 800 million years in between. That's a huge amount of time. But I think that there's probably a structural control in the weakness under this area that allowed the bushveld pipes to come up, then allowed for the Pilanesberg pipe to come in 800 million years later. Because those planes of weakness won't have gone away. So I think there's a vague relationship just on the structural position. Yeah.
I had the same question.
Maybe a question from the live stream.
Well, I forgot about that.
Someone asked, where does the water in the cliffs come from? And then you also almost have to wrap it up. The food is nearly ready. So.
There's a lot of water in those cliffs, isn't there? Which best shows it? Just keep going. The latter ones. Yeah, that much. That's a really good question. Because in terms of catchment, for all of that water that's sitting in the Close Conquani, isn't it? There's a lot of water that goes there, but there's very, very little catchment. But it must be enough to sustain them. I don't think there's any other way that you could get all of that water in there if it wasn't rainwater. I can't really imagine water percolating upwards into the mountains from groundwater. So it must just be rainwater. But I think it's a really good question, because why is there so much of it when you've only got at most 2 or 3 kilometres of catchment area for these?
Sorry, could it not be the aquifer, because you've looked at all the pivot farms in Brits, there must be a big aquifer underneath Brits, which is not far from that.
The way I understand it is, we've got quite an erosion problem as mountains go. We're very aware of erosion here. The soil is actually quite shallow and poor. And most of the layer of soil covering Magaliesberg behaves like a sponge. So the rainwater and stuff is caught up in the sponge, and like a wet sponge sitting on your sink, it seeps out at the bottom. So it seeps into the cliffs.
Right. The aquifer story, that's good one. You can see, going back a few slides. Yeah, you can see vast numbers of pivots. I think that's Brits there, isn't it? You can see all the crop circles like that. By that point, you've got its own bushrock complex. Aquifers tend to mimic in a subdued manner the topography. So if you have a mountain range like Magaliesberg, the aquifer would rise in the mountains, but I don't think it would get all the way to the surface. I think it would be considerable distance below the surface because of the subdued topography of the aquifers compared to the high topography of the hills. So I wouldn't have thought that this was draining straight from groundwater. The idea of the soils, I think, is probably a bit more likely that, yeah, you just get storage so that they keep flowing even throughout the winter. Numerous times now.
I think we can only do one more question because the food's ready.
Chatting.
The light is on, but there's nobody in there.
At Kasmane, the nature reserve in Magaliesberg, there's a green line in the middle, that's a wetland. That actually has water in the middle of winter, like past the rain season, only small ridges on the side. And that's very high. That's the one that's feeding the waterfall.
That's the one that I was. It's actually, if you look at the rocks either side of that, they're in that hole in the syncline. So what might help it is that this quartzite is pretty impermeable stuff. So it is sort of, because you've got the rocks folded into a basin shape, and the rainwater probably will struggle to filter through those rocks down to a deeper layer. So I think maybe any rainwater that does fall is almost obliged to stay close to the surface there rather than sink into any sort of aquifer. So I wonder if there is a bit of a geological control on those wetlands as well.
I'm going to
I'm so glad that your Afrikaner family taught you the good life. So you can share that with
Thank you very much indeed.
Anybody's last questions, we'll be having pizza now, so you can request Adam a little bit for questions, but just not when he's now his food, please. Okay, let's go have home dinner. Thanks.